All right, welcome. Today, we're diving into a material that is quietly, and I mean quietly, changing medicine as we know it. We're talking about polymeric hydrogels, these incredible things that are part science, part sponge, and, all kinds of smart. So let's just get right into it. So let me ask you this. What in the world do your soft contact lenses, a high-tech wound dressing, and the mind-blowing future of lab-grown organs all have in common? Well, the secret sauce connecting all of them, as you've probably guessed, is hydrogels. They are the unsung hero here, and today we're going to figure out exactly how.
At its heart, a hydrogel is actually pretty simple. Just picture a microscopic net made of these long, tangled-up polymer chains. Now, this net is special because it's built from stuff that absolutely loves water. These little water-loving groups just grab onto water molecules and trap them inside the net. And the result? You get this material that can hold a truly shocking amount of water, making it literally a super sponge.
Now, this tech isn't brand new. The whole journey really kicked off back in 1960. That's when scientists cooked up this special hydrogel, PHEMA, and it was a game changer. It was one of the first materials ever designed to be compatible with the human body, and its softness and water content made it absolutely perfect for the very first soft contact lenses. From there, it just exploded into wound dressings in the 70s, and now they're at the very heart of some of the most advanced medical research out there.
So, how do you even build one of these things? And really, how can something that's mostly just water be so darn useful? Well, that brings us to what I like to call the science of squishiness. We're about to see how the way that microscopic net is built dictates, pretty much everything.
Okay, so when it comes to building a hydrogel, you've basically got two flavors. First, you have permanent hydrogels. Think of this like a net where every single knot is chemically welded shut. It's tough, it's stable, it's not going anywhere. Then you have physical hydrogels. These are more like a net held together by a bunch of weak little magnets. If you just change the temperature or the pH, those magnetic bonds can break and the whole thing can kind of melt. A perfect example? Gelatin. It sets in your cold fridge, but melts into a puddle at room temperature. Same idea.
And here's where it gets really, really clever. It's all about tuning. See, scientists can control exactly how tightly that polymer net is woven together. If they create a ton of links, high cross-linking, the net gets super tight. The material is stronger, sure, but it's also a bit brittle and can't hold as much water. But if they use a looser weave with fewer links, you get a much softer, stretchier material that can absorb a massive amount of water. This ability to fine-tune the properties is precisely why hydrogels are so incredibly versatile.
Of course, if you're going to put something inside the human body, whether it's in your eye or on an open wound, it has to be beyond safe. It has to be perfect. Which brings us to a super important word you're going to hear a lot: biocompatibility. Basically, how well do these things get along with our bodies?
So why are they so good at playing nice with our bodies? Well, the secret is in their very nature. Because they're mostly water, they're incredibly soft and flexible, a lot like our own body tissues, actually. That means way less friction and irritation. To our cells, their water-loving surface just feels right. It feels soothing, not foreign, which makes them an almost ideal match for medical uses. But scientists don't just hope a material is safe. They prove it. One of the classic ways is called the MTT assay. It's actually pretty cool how it works. First, researchers put living cells right onto the hydrogel. Then, they add this special yellow salt. Now, if the cells are alive and happy, their mitochondria, the little powerhouses of the cell, get to work and turn that yellow salt into these beautiful purple crystals. So all you have to do is measure how much purple there is. Tons of purple means the cells are thriving and the material is safe. No purple, that means it's toxic. It's simple, it's visual, and it's incredibly effective.
Okay, so we've established that hydrogels are tunable and they're safe. But what can we actually do with them? This, my friends, is where things get really exciting. Let's talk about the incredible real-world power of these materials in healthcare.
One of the biggest jobs for hydrogels is in smart drug delivery. In what's called a reservoir system, you have this core filled with medicine, and the hydrogel wraps around it, like a gatekeeper, letting the drug seep out at a nice, steady pace. Or you can use a matrix system, where the drug is just mixed evenly throughout the hydrogel, kind of like pieces of fruit suspended in a Jell-O mold. In that case, the drug comes out as water gets in and the medicine gets out. Either way, you get this long-lasting, targeted treatment, which is a massive improvement over just swallowing a pill.
But what's really amazing here is the level of control scientists have. It's not just about releasing a drug slowly. Some hydrogels work like a tea bag in hot water. The medicine just steadily diffuses out. That's what we call Fickian diffusion. But others are way smarter. They can be designed to only release their payload as the gel itself swells up with water inside the body. That's called case 2 transport. And by mixing and matching these ideas, scientists can create a release that's perfectly timed for any treatment you can imagine.
And remember those early wound dressings? Well, they have come a very, very long way. Modern hydrogel dressings are incredible. First off, they keep the wound moist, which is proven to make you heal faster. They also soak up any extra fluid and can trap bacteria, keeping the wound clean. But get this, they actually encourage new cells to grow, helping your body rebuild. And on top of all that, they feel cool and soothing, which reduces pain, and many are totally transparent, so you can check on the wound without ever taking off the bandage.
Okay, now for the part that sounds like it's straight out of science fiction, tissue engineering. This is the science of literally building replacement tissues and organs. To do it, you need a few key ingredients: living cells, some biological signals to tell them what to do, and a scaffold, a physical structure for the cells to grow on and in. And what by now do we know is the perfect material for that scaffold? You got it, a biocompatible, porous, water-filled hydrogel.
But for a scaffold to actually work, the little details are absolutely critical. The size of the holes in that hydrogel net has to be just right. And it turns out there's a magic number. The pores need to be bigger than 80 micrometers. Now that sounds tiny, but it's the perfect size. It's big enough to create little highways for cells to move in and start building. It's big enough for channels to form that deliver nutrients and take out the trash. And most importantly, it's big enough for new blood vessels to grow right into the structure, a process called angiogenesis, which is what truly brings that new tissue to life.
So let's just recap. We have a material we can tune for strength. We can use it to deliver drugs on a super precise schedule. It helps us heal faster. And it can provide the literal framework to build new tissues from scratch. We can even 3D print these scaffolds for organs and use them to deliver genes. Which brings us to one final huge question. If we can do all of that, what is the ultimate limit here? What's the end game for regenerative medicine? It's something to think about.